This is recording 1B in our series on quadratic inequalities in one variable. We'll be following up recording 1A with another way of solving a quadratic inequality, this time by graphing the corresponding function. In our last recording, we solved this inequality, 2x plus 1 times x minus 1 greater than or equal to 0. We found that the solution intervals were x less than or equal to, and it was an equal sign because the negative 1/2 made it equal to 0 here. And we had x greater than or equal to 1. Over here, I've got a sketch of the graph y equals 2x plus 1, x minus 1. We're going to use that graph to come up with these same solutions. Let's first of all look at the values of the x-intercepts. Got an x-intercept here at negative 1/2. And we have another one at x equals 1. Those are the same values that we have for our intervals, to start our intervals. Negative 1/2 right there, and 1 right there. So the x-intercepts give us the endpoints of our intervals. Now we just need to figure out from our graph, do we go to the right, do we go greater than or equal to 1, or do we go between negative 1/2 and 1, or do we go less than or equal to negative 1/2? Well, the key is right here. We have greater than 0. Greater than 0 means positive. So we're going to look for where are the y values positive on this graph. Let's see. On this part of the graph, the y values are positive. And on this part of the graph, the y values are positive. In other words, for example, if I put in 2 for the x into the function, I should get a positive value. Likewise, if I put 2 in for the x in this inequality, I will get a true statement. So those two positive portions, if we project them down onto the x-axis, give us the same intervals we have on the number line. The graph is positive at the same time that the inequality will be positive. The graph is positive back here at the same time that the inequality is positive. So I marked those intervals. The graph is positive when x is greater than 1. It's also equal to 0, which is what I want in my inequality. It's also equal to 0 when x is equal to 1. So the entire interval there is x greater than or equal to 1. Likewise, back here, the graph is positive when x is less than negative 1/2. It's equal to 0, the same as the we want for the inequality, when x is equal to negative 1/2. Now, as a reminder, the solutions can also be expressed in interval notation. Okay, they don't just have to be expressed in inequality form. I'm not going over interval notation here, I'm just using it. You can see the appropriate recording for Math 1201 on interval notation. But it basically works out to x belongs to at negative infinity to negative 1/2, round bracket for negative infinity because it's not included, negative 1/2, square bracket. Union, that means together with, the other interval starting at 1 and going to infinity. Repeating the exercise for this inequality, the only difference is that there's no equal sign, but there's still a greater than 0. So I'll still highlight the same portion of the graph because I'm interested in where the y values are positive. I'll circle the x-intercept of 1 because I don't want that included. I'll circle the x-intercept of negative 1/2 as well. And otherwise I shade. So my solution intervals are x less than negative 1/2 or x greater than 1. The interval notation version is the same as in the previous example, but we use round brackets here and here because the negative half and the 1 are not included. Let's take an example from start to finish. Solve x squared minus x minus 12 less than 0. We'll write the corresponding function, y equals x squared minus x minus 12. Then we have to find the x-intercepts. So you find the x-intercepts by putting in 0 for the y rather. I can factor here x minus 4, x plus 3, and I've got my x-intercepts at 4 and negative 3. A quick sketch of the graph is sufficient for this problem. We have an x-intercept at 4, we have one at negative 3. We'll circle those values because we don't have an equals here in our inequality. For our purposes, it's enough to know that the graph opens up. We don't need an accurate location for the vertex, so a quick sketch like this is good. I'm going to be looking for where the y values are negative. So I highlight the portion of the graph where the y values are negative, like so. Therefore, the number line interval that I want is this one. So I just repeat it up here. So we show the interval on the number line, and therefore we write our solution. Negative 3 less than x less than 4, or in interval notation, x belongs to the interval from negative 3 to 4, not including negative 3 and 4. Key idea is to solve a quadratic inequality in one variable. By graphing the corresponding function, identify the values of x for which the function lies on, above or below the x-axis, depending on what you're interested in here. And if there's an equal sign in the inequality, make sure you include the x-intercepts of the corresponding function in the solution intervals.